Alright, physics time, chapter 11, numbers 3 through 11, oddsies. So number 3, 140 kilogram hoop. So if it's a hoop, then talking about kind of maxed out rotational inertia of mr squared. Rolls along a floor so that the hoop's center of mass has a speed of 0.150 meters per second. How much work must be done on the hoop to stop it? Well, the amount of work it takes to stop it is equal to the kinetic energy that it has, right? Got to change the kinetic energy from whatever it has down to 0. So I guess that's going to be negative work, so put a negative sign there. Work is energy, so you want to stop it, you got to take all the energy out. So how much kinetic energy does it have? Well, it's got the kinetic energy of translation plus the kinetic energy of rolling. So that is 1/2 mv squared plus 1/2 I omega squared. If you think that when I write these things out when I'm doing the homework assignments, if you think I'm just writing out these steps just for your benefit because, you know, I'm a teacher and you're a student and all, I'm writing these out because this is the way it should flow. Like, you don't want to skip these steps. You want to communicate what physics you are doing. So sure, I'm the physics teacher and I'm writing it out in a way that I want to be as instructive as possible, but you should do the same. Okay, so for this, I've got 1/2 I, which is m and if you're thinking, wait, I need to know what the radius is. No, you don't, actually. Why am I putting this over? What am I doing? 1/2 I, which is mr squared. Oh, my goodness. M r squared. There we go. Sorry about that. Can't talk and do physics at the same time, I guess. 1/2 I omega squared. Omega is v over r. There it is. So the r squareds cancel out. And so what do we got? 0.5 times 140 times 0.15 squared. That's the translational kinetic energy plus 1/2 times 140 times 0.15 squared. And if you notice, we actually are doing the same thing. In this case where excuse me, you have a hoop and you've got the full mr squared rotational inertia, you get the rolling kinetic energy is equal to the translational kinetic energy. That is a special case where that's true. If it's anything else, then there's not as much rotational kinetic energy. So that's 3.15 joules. So how much does it take to stop? The work necessary to stop the thing is going to be negative that. All right, number 5. 1,000 kilogram car has 4 10 kilogram wheels. When the car is moving, what fraction of its total kinetic energy is due to the rotation of the wheels about their axles? Assuming the wheels have the same rotational inertia as uniform discs of the same mass and size. So discs, so we're talking about mr squared for those. Why do you not need to know the radius of the wheels? We already know that. We just did that here. So the total kinetic energy is equal to the translational kinetic energy of the car, the whole thing, plus 4 times the kinetic energy, the rotational kinetic energy of a wheel. So that's the total, and that's going to be 1/2 mv squared plus 1/2 I omega squared. And I'm going to actually go ahead and, before I plug any numbers in, I forgot my 4 there, because there's 4 wheels. 1/2, this is the mass of the car. 1/2, the rotational inertia, they're saying to treat them like disks. So 1/2 m of a wheel, v squared, omega squared rather, so that's, oh sorry, I'm kind of doing the same messy thing I was doing there. So that's radius mr squared, that's the rotational inertia, times v squared over r squared is the same as omega squared. So there's the answer to the why do you not need to know, because it cancels out. So that all simplifies to 1/2 mass of car times velocity squared plus, let's see what we have here. I got 4 times 1/2 times 1/2, so that all cancels out. And then I got mass of wheel times velocity squared. That's the total kinetic energy. And now finally I plug my numbers in. That's 1,000, mass of car. It's going... oh, they just want to know the fraction of it, so I don't know the speed, so just leave that as v squared plus the mass of a wheel times v squared. So that's 510 v squared, and then the kinetic energy of the wheels is just this part. So what did they want to know? What fraction of its total kinetic energy? So 10 out of 550, or 1 out of 51. Check that in the back of the book. Yeah, 0.02. That says a 1/50th. Or 1/51st. That would round to that. All right. So not much. Most of the kinetic energy is in the car. And that's because it's only the wheels that are rotating. So that's 40 kilograms versus the 1,000 kilograms of car total. So it shouldn't be too surprising. And that's what we get. The number 7. The number 7, we've got a picture. It looks like somebody's rolling bowling balls off the roof of their house again. Ooh, except it's 12 kilograms. Ain't going to find a bowling ball that massive. Yeah, don't try this at home. So, solid cylinder, the radius is 10 centimeters, and its mass is 12 kilograms. Its rotational inertia, they're saying it's a solid cylinder, so that is telling us that we've got a 1/2 mr squared. Rolls without slipping. 6 meters down the roof. It is inclined at an angle of 30 degrees. What's the angular speed of the cylinder about its center as it leaves the roof? Okay, so I want to know what the speed is. I could find the acceleration and then use kinematics, but I am going to go ahead and do this. Since I'm just looking for that speed, I am going to do it with energy considerations. I could just pull one of these equations out of my notes, I guess, but I think you need to have practice here going through the process of this. So the cylinder has gravitational potential energy, and that's going to turn into rotational and translational kinetic energy. So here, that's mgh is equal to translational is 1/2 mv squared plus rotational is 1/2 I omega squared. mg, the h here is this, which would be the sine component of the 6 meters. That's 3 meters, is equal to 1/2 times m time, you know what, I'm just going to leave that as an m because I think that's going to cancel out, isn't it? Mass doesn't matter. V squared, the v is what I'm looking for, plus here I've got 1/2 times I, it's a disk, times omega squared. So those cancel. So I've got 1/2 mv squared plus a quarter of an mv squared. So the m's cancel out, and I get 3g is equal to 3/4 of a v squared. Is that right? I think that is correct. If you're wondering about the dimensional consistency of this, remember this 3, I'm being lazy here, not including the units on everything, because I think that gets too messy. This is 3 meters. So meters times meters per second squared is meters squared over second squared, so that is a velocity squared. So we're good. So v is equal to the square root of, when I multiply both sides by 4/3, I get 4g, right? So the velocity is the square root of 4 times 9.8, about 6.3 meters per second. And was that part A? Yes. Just going to check that before I go on, just in case. What? Oh, the angular speed they want for that. Okay, so this is the that's the velocity, and of course v is equal to omega times r. So that means omega. Oh, sorry, that's the wrong. Well, whatever. So omega equals v over r. So 6.3 over the radius is, so 63 radians per second. Let's check that. Oh yeah, that's right. And then B is, where does it land? So the height's 5. This is a kinematics problem now. Let's see if I can fit it in here. So I have vertical and horizontal. It's going to be launching here at an angle downward with an initial velocity, initial speed, I should say, of 6.3 meters per second. But that's not vertical. That's the combination of vertical and horizontal. So this is 30 degrees, so this is going to be half that, because the sine of 30 is 1/2, and then this is going to be 6.3 times the cosine of 30, which is about 5.46 meters per second. And this is down, So just be careful there. So in the vertical direction, I have an acceleration of negative 9.8 meters per second squared. I have an initial velocity in the down direction of 3.15 meters per second. Final velocity I don't care about, and I'm not looking for it either. The delta y is 5 meters in the down direction. And I'm going to need to find the time here so that I can import it over to here. And I don't know why I started to write something there. So I can find the delta x. The constant horizontal velocity is 5.46 meters per second. Okay, so here, the equation that binds these things together is this. So minus 5 is equal to minus 4.9 t squared minus 3.15 t. I'm going to solve that by graphing, and I'm going to flip all the signs to positive. Well, not all of them. I guess I'm going to add that over. Or maybe I'll add these two to the other side. How about that? So, what do we have then? I've got 4.9x squared plus 3.15x, and then that 5 is still going to be minus. What would a window, what would make sense here? My x-axis is time, so from times 0 to how long is it going to take? Not more than 3 seconds. I think that'll work fine. Negative 3 to 3, I'm just looking for where it crosses, so I think that should be fine for a window. There it is, somewhere between 0 and 1 second. So I'm going to look for that 0, and left bound and right bound between 0 and 1. 0.739 seconds. And then the delta x is just the constant horizontal velocity times time, which is 5.46 times 0.739. So about 4 meters. And let's check that. Yep. All right. Great. Number 9. Oh, this looks like fun. So in figure 1133, these people have graduated from rolling balls off of their roof. They found this to roll balls off of instead. A solid ball rolls smoothly from rest. It's a solid ball, so remember that, which kind of rotational inertia we're going to have to use. Until it leaves the horizontal section at the end of the track at a height of 2 meters. How far horizontally from point A? So this is real similar to what we just did. It's actually easier because it's a horizontal launch. So slightly easier. Okay, so all of the energy stuff, we don't care about anything except for the change in height. So when we do this, all the extra up and downs don't matter. I usually put that one first. I don't know why I did it that way this time. So I have mg times the change in height of this thing. It goes from 6 meters to 2 meters. So that's going to be 4. And the rotational, 1/2 I. What is the I? I should be doing this. I'm setting a bad example here before I start plugging anything in. Okay, so 1/2 I for a, is it a solid ball? That's 2/5 mr squared plus 1/2 mv squared. And the m's cancel out. 1/2 I omega squared. I left that out there. And the omega is going to be v squared over r squared. So I have 1/2 times 1/5, times 2/5, sorry, which is 1/5. And the r squareds are going to cancel. So 1/5 v squared plus 1/2 v squared. 1/2, if you convert those both to tenths, that's 7/10. Multiply it over to the other side is 10/7, so that's 40 g over 7 is going to be the velocity squared. So it looks like when it gets to that horizontal launch pad, after descending 4 meters, it's going to have a velocity of 40, square root of 40 g over 7, about 7.48 meters per second. But they have 7.5 in the back of the book. And, oh, that's not part of the answer. They just want to know. So now it's being launched from 2 meters high horizontally. So vertical, horizontal, acceleration here is negative 9.8 meters per second squared. Initial velocity in the vertical direction is 0 because it is a horizontal launch. Easy mistake to make to want to put that there. Final velocity, don't know, don't care. The delta y is going to be negative 2 meters. It's going from here to here. And I'm going to find the time. And then I'm going to import that time over here. And so I can find the delta x. Okay, so same equation. Delta y equals 1/2 at squared plus vit. This term's gone now. That's 0. So delta y equals negative 4.9 t squared. So t is equal to the square root of 2 over 4.9, which is 0.64 seconds. And then if you want to know the delta x, you must multiply that by the constant horizontal velocity. So it's about 4.8 meters is what I'm getting there. Check in the back. This is number 9, right? 4.8 meters. Looks like I'm on a roll. Get it? Because this thing was like rolling on a roll. All right, so number 11. We got this wagon wheel kind of thing. A horizontal force of 10 newtons is applied to a wheel of mass 10 kilograms, radius 30 centimeters. The wheel rolls smoothly on the horizontal surface, and the acceleration of its center of mass has a magnitude of 0.60 meters per second squared. In unit vector notation, what is the frictional force on the wheel? What is the rotational inertia of the wheel about the rotational axis through its center of mass? Okay, so this is a little different. That's good. So let's see what we can do here. The angular acceleration of this thing, angular acceleration, is equal to A over R. Right? Right, because it's not slipping. And so what is that? That's going to be A over R is at 2. 2 radians per second squared. And what are the two things that they're asking us for? What's the frictional force on the wheel? So if that's true, then let's see. So Newton's second law, let's see what we can do with Newton's second laws. Sum of all forces equal to mass times acceleration, and sum of all torques is equal to I alpha. So I'm guessing probably that we need to do this one first to find the frictional force, and then this one second to find the rotational inertia. So let's see how that works. So sum of all forces here, I've got this applied force minus the frictional force. And gravity and the normal force would be canceling each other out. So if we wanted to make a diagram for this, it would look like this. There's my applied force. It's rotating, so that friction force, if there was no friction, no static friction, then it would not rotate. And then we have the normal force and the gravitational force. I just scooted that over a little bit because I don't like to see them, I don't like them to be overlapping, to see the two forces coming from where they are applied. So those cancel each other out. So the net force is applied force minus friction. And I think we have everything that we need here, right? So 10 newtons minus the friction force is equal to mass times acceleration. That's 6. So looks like the friction force is 4 newtons. That's part A. And then in part B, the sum of all torques, this is the only force that's causing any torque here because that's acting on the center of mass. So that means friction force times the radius, because that's how you do torque, force times radius, is equal to the rotational inertia, which is what we're looking for, times alpha. I was going to put the 2 there, but I guess I haven't plugged in any numbers yet. So friction force is 4, radius is 0.3, rotational inertia is what I'm looking for, and the angular acceleration is 2. So dividing the 2 over there, it's going to be 2 times 0.3, so it's 0.6 kilogram meters squared. Let's check those answers. Oh, yeah. Oh, in unit vector notation. Blew it. I blew it here. They wanted this in unit vector notation, so that is going to be negative 4I newtons. So close. So close to free pizza.